Hello everyone. Some of you expressed a concern or difficulty with the first question of assignment number 7. Okay, and I asked if I can provide additional video tutorial here for this question. So there you go, and I'm making one here. As a matter of fact, this question asks the TA to provide some hints into this tutorial. This is actually one of the reasons that I would like you to go to the tutorial. Okay. Even though tutorial is not mandatory. So anyway, let's take a look at this question here. You have a shaft here with pretty detailed dimensions, giving you the fillet radius at each one of the shoulder, right, and also the radius of the groove. So 0.1 R means the radius right here is 0.1 inch. Okay, so that's what it means, right? Here is this. And this means where you have the bearing location. Okay, so the question, okay, the key point of the question here. Okay, so let's look at these two conditions. So what it says here is shaft is the material, and this is at a steady state speed. The gear transmit a radial load of 230 pound force and a tangential load of 633 pound at a pitch diameter of 8 inch. So what does that mean, right? That means this is where the gear is located. Essentially, the gear located here, okay, with the center at the center of the K-sit. Okay, then if you look at from a side view here, okay, so it says the gear is transmitting a tangential force, right, which is basically what we call the transmitted load, and also there is a radial load, which is WR. So WT equals to, what is WT equal to? WT equals to 633, WR is 230. Right. So this is a tangential force and transmitted load. Now your shaft, right, is in the middle of here. Okay. So the first step that you need to do is, okay, from here, what is the loading condition to the shaft, right? Essentially, you want to draw what's the bending moment diagram and what is the torque diagram distribution along the shaft. Well, okay, bending moment first of all. Bending moment comes from the loading, right, the force. So you have these two forces here, and as we have done, okay, if this is a shaft here, right, and I can move these two forces essentially to the center in here, right? Well, that's not enough. If I move this one over here, I also need to move the torque, right, because this WT also generates torque around the shaft here, right, and the torque is this direction, right? So T equal to WT multiplied by the half of this pitch diameter of the gear, right? So D is given, so you should know what the T is, right? Okay, so that's the loading condition at this point here, right? So now let's go back to the shaft along here. Okay, so then you have WR and WT here. Okay, now you can draw a bending moment diagram in two planes. That's not a problem. You can then combine them two together, right? That's one way of doing it. And also the other way of doing it is you can start from a combined loading force. Well, those two are vectors. Then this is a W, right? So W equal to square root of W squared plus WR squared, right? So that's your W. And now this W, right, will be applied to the shaft and will be perpendicular to the shaft, right? So really it doesn't matter which direction is applying, and as long as we know that it's applying at this location, right? So let's say this is your W. Okay, yeah. There. you don't have any other forces. That's the only force acting on the shaft, right? Now, because of this force, then you say, okay, what are the loading conditions? Okay, this is a force, and you have two bearings, right? Okay, then at this two bearing location, you will have two supporting force, right, coming out from the bearing. Okay, then what is this R1 and what is this R2, right? So that you can calculate using the equilibrium equation, right? Once you calculate this out, and you will find, okay, then what is the bending moment distribution along the shaft? And apparently it's going to be a triangle like this, right? So let's see, what we do is we're going to start from the center of the bearing at these two locations. Okay, that's where your supporting forces are. Okay, so here's how you find the bending moment diagram. Once you find R1, R2, right, then you have your bending moment diagram. And if you're interested in the bending moment anywhere along the shaft, and you don't really have to draw everything out, you can always use the value of R1, R2 trying to calculate the bending moment along at any locations. So the question is, simple question is, okay, this is your bending moment distribution. Then you look at the location from this location to this location, okay, from the end of this one to this one here. So this portion here, you have a bending moment essentially 0, right? Because there's no bending moment at this location, okay? So you should be able to find this out, and what you can find out is, right, there will be this much here at these different locations, okay? Yeah. So the other thing that you need to find out is, okay, well, you also need to find what is the torque diagram, what is the torque distribution along the shaft, okay? Now, if we look at the given condition, the question says the shaft is driven by a gear at the right kV and drives a fan at the left, okay, kV. Okay, so which means you have a fan mounted on the left kV at here. So generally the mounting location will be the center of this kV. Okay, so which means what? Which means if the shaft wants to be in balance, right? So your input torque is here, your output torque is here, right? It's balanced. So between this location and this location there, and you have a constant torque distribution. And how much torque is that? This one here, T equal to WT d over 2, right? Okay, so that's your torque. So that's why you see we have a torque distribution diagram like this. Okay, so in the assignments you have a detailed dimension given like this. So essentially, as you can see that from this location is what we indicate as the supporting location of the bearing, right? And also this line here, right? This line here. So this line here, right, is where the center of this, where the fan is mounted. Okay. So your bending moment distribution is between the support, the center of the support, and this A bearing to the B bearing, and your torque distribution, right, is between the fan and the location of the gear. Okay, so that's how you find these two. Okay, so why do you need this two, right? Why do you need this? Well, you need this because you're analyzing the shaft, which means you're trying to analyze what's the safety factor, right? And also this. Well, so let's look at, so what does safety factor really is? What's a formula for safety factor? The question asks to give you the question says is to use a D.E. Gerber to calculate or to analyze the shaft safety factor, right? So the D.E. Gerber equation is, okay, is here. So this is your safety factor. Okay, so we're not using this one here. Okay, so we know our D, huh? Yeah, at the given location we know our D. Okay, so A and B, so we need to basically fill in all the blank here, right? SUT you will be able to find out. And D, you know, for the location that you're interested, you have the D. So what about A and B, right? So A and B are related to the bending moment, the alternating bending moment component, the alternating component of the torsion, the mean component, and the mean component right, for the torsion and the bending moment. KF, KFS, they're just the fatigue stress concentration factor, right? So we need to figure out all of this one here, right? Okay, so the question give you some hints here. So what are the critical location that you most likely want to analyze, right? Okay. So as we said in the class, generally the key seat provides a pretty high stress concentration. So if there's a key seat, then you probably want to look at it. So we have two key seats here, so we probably want to analyze C location and D location. Also, the location of a groove, okay, will also have pretty high stress concentration too. So we would like to look at this location. The shoulder location at here, this F, okay, is probably also of our interest at here. So maybe we should look at it too because it's pretty close to the maximum bending moment location. So we should look at this one here. Okay. Now for the fillet location here and here and here, they are maybe not that critical. And in reality, you may also want to look at it, but in this case, okay, so we'll just look at the C, D, E, and F. Okay. Yeah. Okay. So D location, right? And apparently you have a maximum bending moment and you have a key seat, so that's probably the worst situation in here, right? So let's look at the D location and all of these locations. Maybe let's first look at this. Let's look at a simple one here. Let's look at the C location, right? If you look at the C location, okay, and first thing you want to see is what's the loading condition at the C location. Well, here is your bending moment and torque diagram. And apparently at the C location, you don't have any bending moment. All you have here is a constant or steady torsion or torque, right? 2,532. So which means that at the C location, you only have a steady torque T, or which means Tm. Okay. As a matter of fact, at this location, you don't even have to use this dE torsion here, right? Because what you have here is not a really fatigue loading at the C location. What you have here at the C location is a static, okay, at the C location. Okay, so you just need to analyze what's the shear stress at this C location, which is TR over G, right? And then you can use the this is ductile material, and use the static MSS to analyze the safety factor at the C location, right? Okay, so C location is a static, okay? So tau equal to TR over G. You can use MSS to calculate the safety factor. Okay, so now let's look at the D location, right? D location, you have a key seat. Now the question didn't tell you, right, what the fillet radius is at the key seat, right? Now you do need that information. Why is that? Because, right, if at the D location here, so what we can see is, now first of all, if I want to use, okay, this equation in here, right? If I want to use it, I need to calculate A and B. Then what is the value of MA? What is the value of MM? What's the value TA? What's the value TM? Right? So from the torque diagrams, you can see that, well, D, there's no alternating component for TA. There's only TM, right? 200, how much is that? Yeah, 205,032. Okay, and MM, right? MA. Well, this is a D location. You have a basically constant force, right, and rotating shaft, which means you have a complete reversed, right, bending stress. Okay, so really this term is 0, and you have MA, which is, right, this value at here. Okay, there. Now you get this too. You also need to figure out the key F, KFS. So key F at KFS what does that relates to, right? If you recall, that KF equal to Q KT minus 1, and KFS equal to 1 plus QS KTS minus 1. Okay. Now, since this question didn't tell us what fillet radius is, okay, and what we can always do is we can use our table. Okay, this is table 7-1. Okay, you can use this one here for the end mill K-sit. Okay, find the bending, KT, and torsion. Now this is in the A set. This should be 2.14 here. Okay, this is in ninth edition. This is the old edition here. Okay, so KT, right? In this case, your KT equal to 2.14, and KTS equal to 3.0. Okay, and under a condition R over D equal to 0.02. Now, why do you need this? Because you need that for the Q. And Q, right, depends on the R. Okay, and you can always use that Newberg constant, okay, to calculate. Okay, if I recall this one here. Now, this is where you can recycle your Excel sheet. You know, I did provide you a formula sheet and lots of a template, so you don't really have to calculate this, right? You can just simply plug in the number of R, and then you can calculate that. Okay, so I think you can find some of this. Let me see. Endurance limit. Yeah, this is a good one here. Yeah. There, in this template here, you know, I do have here. You want to just change this R, and you'll get the corresponding Q, QS, and the KFS once you plug in the right KT, KTS, right? So you have a formula of this. Okay, it can save you a lot of time here. Okay. Well, then what is R? R equal to 0.02 D. So what is D? Right, at this location, the D equals to 1.75. Okay, so which is 0.02, 1.75. And then from R, you can calculate Q, and also you can calculate QS, right? So you have a similar formula for the QS. So once you know QQS, you'll know what the KFS is, right? Then you completely know what A and B is. So back to this question here, all you left with is SE, right? So how do you calculate the SE? So this is the drill that you have done many times, right? To calculate SE, right, equal to KA, KB, and SE prime. I didn't give you any other condition here, so I think you just have to calculate KA and KB, right? So yeah. Now Ka is surface condition, surface factor. KB is the size. Okay. So size, you have a D, so you know how to do that. Surface, it's a co-joint, so you can use that table to find the surface factor. Then you can find SE, right? SE prime is half of SUT. Okay, there. So now you can completely calculate the safety factor, right, at this location. Okay, I didn't provide you any formula for this one here. Okay, now I'm still trying to prepare for tomorrow lecture, but I guess, you know, if I have time, I can get ready for some of this one here, but I don't think that's too much. You can always prepare in an Excel sheet for a set of all different kind of safety factors. Okay, so I think it's not that difficult, but I did for this question here, I did use a MATLAB to trying to confirm the solutions are right. Okay, yeah. The solution, you know, is not exactly, you know, the number. Not shouldn't, if you get a little bit, I think this one here, n is finite. If you get n equal to 3.6 something or 3.5 something, you know, it should be pretty close. Okay, yeah, should be pretty close. So anyhow, so that's how you do the location D, right? And I think you should know now how to location E and F, right? For location E, we did a similar example in assignment number 6, I believe. I think here you need to look at for location E. Okay, you need to look at the appendix table 8-15. Dash 14, okay, for the KT, okay, for the KT. Yeah, you look at the E here actually, right? Now why don't you look at the KTS? Well, the reason is because there is no torsion at location E, so don't worry about this, right? There's no torsion. Okay? Same thing for the location F. There's no torsion at location F. Okay, right? So this is why you can simplify the situation. However, you do have a fatigue situation at the location E and location F. Okay, so that's how you calculate. I think that's all I wanted to talk about, and this is actually a pretty good example how you would approach in terms of your shaft design. Okay, and of course, you may not have the dimensions ready, right? You need to figure out the dimension first. Okay, from a safety factor, so it's the other way around. However, you do need to analyze what the critical location for your shaft, right? So the first step is always very important. So what is the bending moment and torque distribution along the shaft? Okay, in your case, let's see for the design project, okay, you do have two shafts, right? So one is carrying the pinion, okay, and the other is carrying the gear, right? Okay, so you just like that shaft over there, okay, and if you're using spur gear, and then for each one of the gear, you will have a loading, right?